So I'm going to tell you about a theorem. It's a theorem of pure convex geometry, but it's motivated by the interpretation of a compact convex set, such as the set of density matrices or the probability simplex, as the state space of a system, perhaps a physical system, perhaps another complex system we're interested in. So the theorem is, my co-author is Joachim Hilgert. There's the archive reference. Any finite dimensional compact convex set that is one, spectral, and two, strongly symmetric, and I'll define those terms, is the space of normalized states of a simple Euclidean Jordan algebra, or a simplex. And we're working in finite dimension. We believe there are infinite dimensional generalizations of this. So this is already very close to quantum state space. And in this game, we're often interested in characterizing quantum state space in physically significant or informationally significant terms in order to understand it better. All right, so Jordan, von Neumann, and Wigner classified these state spaces, the simple Euclidean Jordan state spaces, and they're just complex, quaternionic, and real quantum theory, three-dimensional octonionic quantum theory, and any theory whose systems are balls in however large a finite dimension you want. Okay, I should say our theorem is related to one that I was also involved in with Marcus Müller, who's here, and Kaz Ududek. There we had one more assumption, which turns out not to be necessary. And the assumption is that there's no irreducible three-path interference, a notion we adapted from Raphael Sorkin. There's a couple of ways, which I'll discuss later, of getting to complex quantum theory from this already very close class of Jordan algebras. One is called energy observability. The other is local tomography. But let me proceed to define the terms in the theorem first. So on this approach, probabilities of outcomes of measurements are given by affine functionals whose values on states in the state space are probabilities. So they're bounded between 0 and 1. And I've given a few examples here, which maybe I'll discuss a little bit. This one on the left would be a real quantum bit. It would have to be the block ball in 3 dimensions if it were a complex quantum bit. And I've just shown the 1 and 0 constant surfaces, value surfaces of an affine functional. If both the 1 and 0 touch the state space, then measuring that functional and the unit functional minus that functional distinguishes perfectly those states. So in general, a measurement outcome is a list of such functionals, which we call effects, that add up to the constant functional whose value is 1. Each element of this list corresponds to a different outcome of a measurement. And then we say a set of states is perfectly distinguishable if there's a measurement E sub I such that E sub I of omega j is delta ij. We can tell exactly what state was prepared if we know you prepared one in this list. Okay, using this concept, we define spectrality. Oh, sorry, yes, so we define spectrality. We say every state of the state space can be written as a convex combination of a set of perfectly distinguishable pure states. By pure, we mean extremal in the convex set. Cannot be written as a non-trivial convex combination of other states. We also have our second assumption, strong symmetry. Every list of perfectly distinguishable pure states transforms to any other such list of the same size reversibly. And by reversibly, we mean it's an element of the affine automorphism group of that compact convex set. So, in quantum theory, omega, the state space is the density matrices. Rho goes to U, rho dagger. That's an example of such an automorphism. Transpose is also an automorphism, although we rule it out for other reasons. Okay. So these two things just generalize the spectral theorem for density matrices and the fact that any orthogonal set of rank 1 projectors can be taken to any other such list by a unitary conjugation. And it's sort of remarkable that this set of properties gives you something so close to quantum theory. If we want to actually get complex quantum theory, we could add, for instance, energy observability. We say there's non-trivial continuous dynamics, reversible dynamics, and there's a one-to-one relationship between those and observables that are conserved by the dynamics that they generate. Kind of a Noether's theorem type thing. So 2 axioms to Jordan, 3 properties to quantum theory, and they're very significant in their applications in quantum theory and have a lot of intuitive appeal. Thanks.